All right, so can you all hear me okay? Oops. Can you all hear me okay? For a second there, I was muted. Okay. So, so this will be our lab portion of the course. And again, there won't be any mandatory lab meetings. I will record these sessions and put them on Zoom. I'm also recording this with my camera, but I noticed a couple times during my lecture today, I accidentally hit the stop button on my lecture. So if I actually need to post that lecture online, it will be kind of broken up. The Zoom will be fine. I think the first thing to ask you, do you have any questions? You saw the video that I asked you to look at on Canvas, I hope. Do you have any questions regarding the lab? No questions or concerns? So let me recap. You're going to be doing, this semester is going to be different in terms of how we do the labs. All your labs you're going to be doing at home. I'm not going to give you any simulations. All right, and I'm really not going to give you any set of data to analyze like we did last year, but last year was a little bit different. You're going to have to do 5 video reports. And 4 written reports. And you're going to basically be graded on those reports for the lab. The grade that you get is separate from the grade from the course, because this is a separate course compared to the 210. So your grade will be based on these reports. Your first video report will be due on September 4th. And it's really not a long, it shouldn't be anything long. We're going to be doing the properties, our first lab is called properties of charge. And it's a very qualitative lab, so basically what you're going to be doing is observing and explaining. And I really feel that the best way for you, especially with this online format, for you guys to do these reports are just do a video report. So what you're going to do is 2 things for this report. There's actually 2 reports for this lab. The first one is you actually have to construct some of the equipment you need for the lab. You can do this right away because the equipment you need to build for the lab can be obtained with stuff you have at home. And I'll show you in a minute. Okay. So your first video report is due on September 4th. I doubt this video will be more than a minute. All you got to do is show me the equipment you built, show that it kind of works. Okay. And I want to see your face in the lab too, in the video. So basically I want to have a video of you showing me the equipment. I want to see your face. Okay. And the equipment at the same time. And just kind of quickly show that it works. And that'll be the first, so this will be worth 20 points, and then the main report will be worth 40 points. My labs are either worth 20 points or 40 points, depending on how long they are. Okay. Now, when you do the written reports, is the equipment, some of the equipment for this lab is in the lab kits. Some of the equipment you'll get from home. So for example, I'll just show you real quick. I'm getting a little bit ahead of myself, but one of the things you have to build is a device called an electrophorus. And this is used for charging by induction. It's an instrument you have to build. in order to do the experiment. So I'm going to show you when I made a real simple one, just to give you an idea of what it's like to build it. Here's mine. Okay, it's a paper plate. You place a piece of aluminum foil over the paper plate, and you glue an insulating handle, in my case a paper cup, and I use PVC glue, you don't have to use that. This is the electrophorus. This takes 5 minutes to build, okay? What you got to do is make sure that it works. So what you want to do is take a piece of saran wrap. You'll see in the experiment, this part of the experiment, you probably don't need any of the lab kits, okay, for electrophorus. You want to read the lab, where you're going to do this, and you just want to demonstrate that this works. So basically what you'll do is you'll build this, and you take a piece of saran wrap and put it on the surface, and you want to rub it with the fur that you get. It's not real fur, okay? You rub the saran wrap with fur, you put this on top of the saran wrap, and you just touch the metal. You pick it up, and you bring your finger towards it, and you probably see a spark or hear something, okay? And then you know it works. And that's charging by induction. We'll talk about that. Yeah, it's very high tech. Okay. But these are things. So you don't need the lab kits for this. Okay. The other device you're going to build is an electroscope. I guess I'll talk about it now. The other device is called an electroscope. Basically, it's used to measure charge. I mean, it doesn't give you a number. It's a device that tells you something is charged, and it allows you to compare whether one object has more charge on it than another. So basically what it is a jar with a conductor, with a piece of metal going into it, and then you have 2 pieces of aluminum foil. You have a cover that's an insulator. So when you bring a charged rod near the top, it doesn't have to touch it. If you bring it near the top, what will happen is, if the rod's negatively charged, the electrons are going to want to run away from the rod. They come down here, so now you're going to have an excess of negative charge on these 2 leaves, and they're going to come apart. That's going to tell you have a charge in the vicinity. The instructions for building one of these are in the lab itself. There's a link to how to build one of these. By the way, there's a lot of websites that tell you how to build these. All you need is a jar, aluminum foil, and do not use the thick aluminum foil. Use the thin one, because you want to make sure that these guys move freely. Okay, so the best ones use gold foil. I don't expect to use gold foil. Okay, so use aluminum foil. Okay, and then just build this, and your video just show that it works. You take a charged rod, you bring it over, and you see these things spread out. That's it. So you're going to have to construct this yourself. And there's a link to a video on how to build it. There's actually quite a few videos on YouTube that tell you how to build one of these. Okay, they're pretty straightforward. So your first report is basically you showing me that you built this, and you built this. Now, some folks, especially you folks who want to be engineers, you might want to do something a little bit better than this for electrophorus. You can get a rectangular plate, or a square plate, made out of aluminum, and put an aluminum handle on it. That's it. Okay, this is cheaper. I went for the cheapest way to build things. So this, and the electroscope is built from things you have at home. I'm assuming you have a jar at home, an empty jar, a small one, like a peanut butter jar, or any jar. It doesn't have to be a big jar, it could be whatever size you want. Okay, and you can build an electroscope. And as we go through this, these few weeks, Tyler will have lab hours. I will have lab hours to help you in building these. Okay. Going back to this, the written reports are your traditional reports that you had done in 205. You're going to do all the good stuff, the air propagation. You're never going to get away from that. Whatever requirements you had in your lab reports for Physics 205, you'll have here. The faculty in our department, the full-time faculty, we're pretty uniform in what we expect out of lab reports. We might grade things a little bit differently, but we expect you to do the air propagation. Nice graphs, okay? So I'm not going to talk about graphs or anything like that until we get to the lab on Ohm's law. Just real quick, what graphing software did you use last semester? Did you use graphical analysis? And you still have access to that? Or Logger Pro, okay. I have another, just in case you have issues, I have another piece of software that you can use. It's free. It's called SciDavis. I have the instructions on Canvas on how to use SciDavis. And so when we get to graphing the data, I will talk about SciDavis if you want to use it. Or I might make a video of it just so I don't spend time in class. But graphical analysis is fun. Basically, I need a piece of graphing software that will give you the results of a curve fit and the uncertainty in the curve fitting parameters. I need that. And graphical analysis does that, and it's easy to use. So yeah, go for it. Now be careful with graphical analysis. So I'll tell you what happened one semester in one of my classes. I updated my computer about 15 minutes before I went to class, and probably some of you guys who had me for Physics 8 probably saw this happen to me. I updated my operating system about 15 minutes before class. I go into my Physics 8 class to show them how to use graphical analysis, and it didn't work. It says, this operating system is not compatible with graphical analysis. So be careful. If you're using graphical analysis and you update, it might not work. Okay. But I have SciDavis for you. SciDavis is actually a more robust package. It does all kinds of stuff. When we get to the last lab this semester, you are going to do a complicated curve fit. SciDavis has the curve fit equation. Graphical analysis, you have to type it in. Yes, that's a good piece of advice. Don't update anything. If you want to keep using graphical analysis, do not update your computer, okay? Because that messes things up. All right, and I didn't listen to that, and that messed me up. But anyway, if you need to, I have an alternative called SciDavis, and the learning curve is a little bit steeper, but it's not too bad. Okay. All right, and we'll get to that when we do the third lab, Ohm's law. So your first two reports are video reports. Actually, no, I'm sorry. Your first three reports are video reports. Okay, and then you'll have a written report come to do. Yeah, you're right. You just got to be careful when you install updates. In my case, it wanted me to install the update operating system. It wasn't a security update, and that's what messed me up. Okay. Do you guys have any questions? Questions regarding, what my expectations are, or no questions? And feel free to blurt out if you something here, whether you want to chat or you can unmute yourself and ask a question. Okay. So just remember, the first video report is due the 4th of September, and it's just basically you have to do buildings. Just a video showing me that these work. That's all. This should be pretty straightforward. The report for the whole experiment, the video is going to be longer. All you got to do is update the video, upload the video. The lab report due on 9/18 is a video. Okay. No, actually, the labs where you have to do standard deviation calculations, those are written. There's this first lab is qualitative. Okay, this first lab is qualitative, and I'll tell you what, if I had to read, because I read 50 lab reports where you have to describe what's happening, it's very difficult. It's much easier for me, and I think for you too, to explain what's happening. It'll actually help you more to explain what's happening when you're doing the experiment. So this report, you're going to demonstrate, and you don't have to demonstrate every single thing, but demonstrate what's going on and explain the concepts that are at work. Okay? That's really what I'm looking for. Demonstrate and explain. Instead of writing out a whole essay. Because I got to read that. It takes forever to read that. Yeah, that's what I should do. I only have two, right now I only have 2 monitors, but I probably need another one. Okay, so let me talk about the properties. Let me talk about properties of charge, because it's what the lab is going to be on. And I'm giving you quite a bit of time, number one, because of the format change, and because the lab kits aren't, you're not going to get till next week. By the way, we are doing several less labs than you would normally do. Okay, just because of the fact that we're online. Okay. All right. So let's talk about properties of charge. So you can kind of do the lab. Some of these things are kind of subtle. So I want to start by really talking about some properties of matter first, because the properties that matter have are based on atomic structure and molecular structure. So, and some of this stuff I've already talked about in class. The basic constituents of matter are electrons, protons, and neutrons. Okay, yeah, I know there's quarks. Let's ignore that for now. Okay, let's pretend we're not at the point where we learn about quarks. Okay, we're learning physics pre-quark time. Okay, so the basic constituents of matter are electrons, protons, and neutrons. And so we have atoms, ions, and molecules. So let me say some things about them. An atom, and now I'm talking about a neutral atom, is uncharged. It has the same number of protons as neutrons. And so if I use the letter Z to denote the number of charged particles, then I can say neutral atom has Z protons and Z neutrons. Okay. And what about, I'm sorry, electrons, geez. That makes the total charge 0 because you have Z positive and Z negative. So for example, helium, the helium atom, abbreviated He, has 2 protons and 2 electrons. The Z is 2 in this case. The sum of the charges is 0. It's neutral. Now, it's true that it has 2 neutrons. The common isotope has 2 neutrons. There's actually a version that has 1 neutron in it too. The mass of this helium atom can be, to a very good approximation, described in terms of the mass of the protons and the neutrons. The protons and the neutrons have approximately the same mass. The electron is very light compared to the neutron. In fact, or the proton. In fact, the ratio of proton mass to electron mass is about 2,000. So when we talk about the mass of an atom, we kind of ignore the electron, okay, to a good approximation. You don't want to be really exact for that end, but we're talking about third or fourth decimal place. So the mass of the proton, by the way, if you're interested. So this is about 2,000 times as heavy. And the neutrons are around in the same ballpark. I forget the value. It varies at this decimal place. I forget what the value is. Okay, so on a helium atom, the electron, or any atom, the electrons are far away from the nucleus. The nucleus consists of this guy and this guy, protons and neutrons. The radius of the nucleus is about 10 to the minus 15 centimeters. I'm sorry, 10 to the minus 15 meters, approximately, in that ballpark. The electrons are about 10 to the minus 10 meters from the nucleus. Okay, so that's a big, I mean, when you scale it up, that's a big difference. So the electrons are really far away. And so when you want to talk about the properties, physical properties of atoms and materials, they're really based on the electrons. It's very easy to take out an electron from the helium atom and make it charge. If you take out a proton from the helium atom, it's not helium anymore, it becomes hydrogen. Can you do it? Yeah, but you need a tremendous amount of energy. The protons don't move very much. It's these things that are fairly easy to move because they're far away from the nucleus. And the electrical properties, thermal properties of materials are based basically on the electrons. What do the electrons do? Okay. Now, if you have an atom that's not neutral, that's called an ion. So ions are atoms that are not neutral. So if I remove an electron from helium, it becomes positively charged because I have two positives and one negative. When you add them together, I have an excess of one positive charge, so I get helium plus. I can take off two protons if I want to. I'm sorry, I can take out two electrons if I want to, and I get helium double plus. The total charge is the charge of the two protons. In fact, there's a special name for them. They're called alpha rays. One of the ways something can decay is by giving up alpha rays. It's basically a helium atom with its two electrons removed. And so that's an ion. And in fact, you can remove a lot of electrons from an atom. You can take uranium, which has 92 electrons and 92 protons, and you can take off 91 of them. You can take off 91 electrons from the uranium atom. And boy, this thing is reactive, okay, because it's highly charged. But that can be done in the lab. However, if you want to add an electron, that's a different story. It's actually very difficult to add an electron to an atom. The most electrons you can add to an atom, and I'm talking about an atom in the gas phase, isolated atoms, is 1. The most electrons you can add is 1. And you can't even do it to helium. Helium is happy in its state. Okay, if you've had chemistry, you know that helium is a Nobel gas. And it's happy in its state. It's very inert. It does not want to pick up an electron, and it doesn't. It doesn't like it. But there's some atoms that like picking up an electron, like chlorine. If they'll pick up an electron, it becomes chlorine minus. And that's the most amount of electrons that you can pick up. In fact, all the elements in the periodic table that are one column to the left of the noble gases love to pick up that electron. They have what's called a high electron affinity. But that's all you can do is pick up one. And there's a lot of atoms that do not like picking up the negative ion. I'm sorry, let me look at your question. Never find an ion with more than one electron's worth of mass. That's for an atom. Okay, right now I'm just focusing on atoms. Nitrogen cannot, for example, nitrogen, helium, zinc, argon, you cannot put an extra electron on them. There's some atoms you can't even put the extra electron. Most atoms you can't. But the most you can put is one. Now, when you start talking about bigger systems, molecules, then there are certain molecules in which you can add the second electron. That's kind of a big field of study in chemistry and physics. It was something I used to do when I worked in Reno. Okay. A molecule is basically a combination of atoms, right? I mean, it's a simple-minded way of saying it. An organized arrangement, a combination of atoms. Like H2O. Or NaCl. These are molecules. And these are neutral. But of course, you can take off one of the electrons and then become ions. Or you can add an electron and it becomes ion. And there are some molecules in which you can add 2 electrons to them. Okay. So you can even have a molecule that has more extra electrons than atoms within it. I can understand your question. In general, you're going to have more electrons than atoms in a molecule, generally. Right? Because each atom has at least 1 electron. More extra electrons. Generally you can have 2. I have yet to hear of a molecule with 3 extra electrons on it. Generally 2. Okay, doubly charged, they're called doubly charged negative ions. Or dianions. That's what they're called. And people study them. They're like, why only 2? No, that's of course why only 2. Okay. Now, there's a special type of molecule in which a bunch of atoms or a bunch of molecules are clustered together. So you can actually in the lab make something like this. You can make these. Those are called clusters. They're special types of molecules. Okay. So these are named clusters. So this is the famous one. It's called a buckyball, C60. Once this was discovered, then the idea of graphene and nanotechnology, that's when it was developed. It came from here. And you can add more than 1 electron to these. The most I've heard of is 2. Okay. But anyway, these are what makes up matter. These are what makes up matter. Matter is made up of atoms and molecules and clusters. Okay. Now, the electrical properties of solids, for example, I'm really going to focus on solids, is really due to the electrons. And so, I'm going to categorize, from an electrical point of view, I'm going to categorize substances either as insulators or conductors. And I'm going to assume, in an ideal case, a perfect insulator and a perfect conductor. There's actually a third group called semiconductors. For our purposes, I'm not going to talk about them. Okay. Okay. So what's a conductor? In a conductor, you have a small fraction of the electrons that are free to move within the material. Why does that happen? Well, when you have a conductor, like in metal, like this rod, the way the atoms interact with each other and the way the electrons interact with the atoms are such that you end up getting some electrons that are free. A small fraction of the electrons in here, and it's really the valence electrons, the outermost electrons in the atoms, that tend to be free to move within it. And when the electrons flow, you can conduct electricity. The opposite case is the insulator, where the electrons really can't flow at all. The ideal case is they don't flow at all. But there might be a few that will flow. And in fact, if you put a big enough charge near an insulator, the electrons will flow. Okay. And what happens is, in that case, you get something called breakdown, and you'll get a discharge, and you'll see a bolt of lightning. You'll see a spark. Okay. But let's assume we're not at that point where we're putting such a huge field near it that they will conduct. So for low enough fields, the electrons won't flow. However, most insulators have a special property, really all insulators have a special property called polarizability, where you can separate the positive and negative charge within the molecules that make up the material. Some materials are already polarized, where the positive and negative charges are separated, like water. Water molecule is called a polar molecule because there's an average. If you look at the distribution of positive and negative charge within the water molecule, you'll see a distribution that's not symmetric. You'll see one side of the molecule has more negative charge than the other side has positive charge. But a molecule that's unpolarized, the plus and minus charge is distributed uniformly within the molecule. So do polarized molecules contribute to any electrical behavior? And really the answer is yes. So let me talk about what happens when you place a charged object near an uncharged insulator. And you might be surprised as to what can happen. Well, let me erase my board. So normally when you have, let's say, a non-polar molecule that makes up a substance, the centers of positive charge coincide with the center of negative charge. What that means is the amount of negative charge and the amount of positive charge is uniformly distributed over the molecule. Now, suppose I take a rod and I charge it. I'm going to talk about what charging means. And I charge it. Can you hear the static? Because I have this by the microphone. Can you hear the static when I rub this? No? Okay, it's not loud enough. Sorry. And I bring it near here, this will be negatively charged. What do you think is going to happen to the charges within that molecule? If I bring in a rod that's negatively charged, like charges don't like each other. And so what's going to happen is you will get an uneven distribution of charge. So the molecules will actually have a separation between the positive and the negative charge. We'll call this distance L. Okay. And I drew the vector such that it goes from the negative charge to the positive charge. And what we've done is we've induced a dipole moment. Okay, what we've induced is a dipole moment. And we define the dipole moment by the letter P and say it's equal to the charges here, these two charges are equal, times L, where L is a vector that goes from the negative charge to the positive charge. But what do you think is going to happen when I bring this object near an insulator? If the positive charge is closer, what do you think is going to happen to this object? If the original object, it doesn't matter where I make this positive or negative. What do you think is going to happen? It should attract. So let me try to demonstrate that for you. So it's going to take me a second to set this up. This is a balancing act. Let me adjust the camera. Hold on a second. All right, you can see that table? So this is a petri dish. And this is going to be tough to do it in the house here. I had a 2x4, and I'm going to balance it. This is a trick in itself. But it worked. That's good. So that's uncharged. This 2x4 is uncharged. So what I'm going to do is I'm going to rub this PVC rod with fur. It's charged, okay? And I'm going to bring it. Do you see the attraction? Let's see if I can bring it back. No camera tricks. Okay? And so it turns out, okay. Sorry about that. It turns out that a charged object will always be attracted to an uncharged object. Okay, so you should probably write that down. That's going to always be true. Okay? I'm ready for it to up. Okay, hold on a second. I'll fix the camera. Okay, let me. Okay, sorry about that. I always have to adjust the camera when I'm doing these things. Okay, so that's going to always be true. And the reason why is because when I bring this object near the insulator, I will polarize the charge in the material so that the charge that's similar to the rod runs away from it, and the charge is opposite the rod gets closer to it. And so you'll have them attract each other. It's not a huge effect, and the reason why you got to see that effect is strongly because I balanced the 2x4 on the little petri dish. Okay. Okay. You guys are all able to see the demo, though, right? I know it was hard to see the writing. You all saw the demo, right? Okay, good. Okay. So there are materials that are whose molecules are polarized, like water. The effect will be stronger. So what you can do at home, you can do this experiment at home. Turn on the water faucet. You get it just in a narrow stream. And then take a comb, rub it on your head. You're charging the comb when you're doing that. And bring it near to the stream of water. You can make it bend. Now what are you doing? You're doing the same thing. The only thing in the case of the water, what happens in the case of the water is the following. Water is polarized. So this is an example. This picture is an example of a polar material. The only thing is when you have polar material, like polar water molecules, the dipoles are randomly oriented. And then when you put this charged rod near it, what happens is you end up aligning the dipoles. And that's where the attraction comes in. Now, my picture that I show in this slide is exaggerated because not every single dipole will be aligned. It just, a large percentage of them will. And so then that's when you get the attractive force between, let's say, the comb and the water. So you should try this at home. Rub a narrow stream of water and then rub a comb on your head and bring it near the stream of water. You can make it deflect. And look at how the effect changes when you look at the top of the stream and the bottom of the stream. Okay. So this will always be true, and whether you have a polar molecule or not. And I'm going to say some more about this next week. I'm going to go into some physics, either next week or the week after, to see where we're at. So let me talk about what does it mean by charging by contact. What does it mean when I do this? I'm taking a piece of fur and a PVC rod. By the way, in your kit, the PVC rod won't be this big. Okay, it's kind of clunky to have on this big. And you rub it, and this gets charged. What's happening? What's causing the charge transfer? Yeah, there's friction involved. And a lot of people say, you go online and you look, oh, it's charging because of friction. You got to be careful. Yeah, friction, the frictional force allows the transfer of charge from the fur to the PVC. But it's not just the friction. In reality, the friction provides a conduit to have the charge being transferred. If I take two materials that are exactly the same and I rub them together, There's friction there, but you won't get any charge transfer. In order for you to get charge to be transferred, one material has to want to give off its electrons, and the other material has to want to accept them. So this material accepts electrons. This material likes to give them off. So friction just gives you provides a way for the charge to be transferred. But it's the electrical interaction between the two materials that really does it, because if the two materials have the same charge, the same properties, you're not going to get any charge transfer. And people have done, they do experimental studies with various materials. And they've come up with something called the triboelectric series. And what they do is they assign a number that represents whether something likes to pick up charge or not, or give it off. I should say pick up electrons, because positive charge doesn't get transferred, only negative charge gets transferred. So, for example, this material, PVC, is at the bottom of the list. It'll be a negative number saying that this object likes to pick up electrons. Rubber is also at the bottom of the list. Materials like silk, wool, they're at the more top of the list. So if you actually look at the triboelectric series, you can Google it online. You can see what materials you can use to rub together to get charge transfer. If two materials have the same electrical properties, you're not going to get any charge transfer between the two materials. So be careful when you talk about charging by contact. Is it really due to friction? And I would say friction only provides a method for you to transfer the charge, but it's the electrical interactions between the two materials that really causes the charge transfer. Okay, so it's a point where you have to be just careful in describing what's going on there. Okay. Now, you can produce a temporary induction of charge. We kind of did that here, but let's talk about it in terms of a conductor. Suppose I have a conductor. Well, let me find a marker that's not red. Let me erase my board. And a conductor is easier. You can see the effects, the electrical effects, more easily because the electrons are free to move. So the effects in conductors are more pronounced. So let's say I have a conductor. It's neutral. And I bring a negative charge in there. Okay, let me rewrite that. What's going to happen to the charge in here? Well, the electrons are free to move. So the electrons in here do not like this negative charge. And so what they're going to want to do is whatever excess negative charge you have, you're going to have move to the other side of the slab. And then what's going to happen on this side is you will have an excess of positive charge. So what you've done is you've actually induced a charge on this surface temporarily. Now, if I remove this, if I get rid of this, the charge will rearrange itself so that the system is neutral again. But you notice there's a dipole inside here, right? You have a separation of positive and negative charge. You have a dipole. It's pointed that way. Okay. What if I do this? What if, while this charge is here, I take a wire and I connect it to the earth? This is called ground. What's ground? Or what's here? Sometimes you say the old term would be you earth it, E-A-R-T-H, or you earthed it, E-A-R-T-H-E-D. What does that mean? Well, the earth, the ground, is a source or a sink of electrons, which means that it can be a drain or like a water faucet, where the water coming out of it is the electrons. Okay. So, what have I done here? I've provided a path for the electrons to go into the earth. So, for example, if I touch my hand, if I put my hand here and I touch the water faucet, because the water faucets are grounded, well, I've provided a path for the electrons to go through me and into the ground. Okay. Now, what happens though? Well, I still keep that there and I remove this. Guess what happens? These electrons go away. And now I have a conductor that's positively charged. This is called charging by induction. That's a permanent induction of charge. Yeah, the Earth is a reservoir of electrons. That's a good way of saying it. The ground is a reservoir of electrons. And some people say it's a source or a sink of electrons. So now I've induced a positive charge on it. If I put a positive charge here, and I ground it, then I would have a negative charge here. Because then you have electrons being pulled up from ground when you ground it. Now another way to induce a charge is this. Suppose I have two conducting spheres. Let's focus on the first one. And this is an insulator. This is a conductor, this is an insulator. And I bring a rod that's negatively charged. Doesn't matter whether it's negative or positive. What's going to happen? Well, the electrons in here don't like this guy, so they come in. And so you're left with a positive charge here. Or a 4 of it. Now, suppose I take my second one of these and I put it in contact. What's going to happen to the electrons? They want to go as far away as possible from this guy, so they're going to come here. Now, let me take this away. What have I done? I've made that positively charged. In fact, the other one's negatively charged and this one's positively charged. So I've actually induced the charge in both objects. And that's permanent induction of charge. The electrophorus in which you're going to build for this lab will test the idea of charging by induction. Because what you'll do is you'll put a piece of saran wrap on a surface. You'll rub it with the fur vigorously for like a minute. You'll put this on top. And then you'll touch the metal to ground. So basically all you got to do is touch this, and then your other hand will touch like a water faucet. You'll lift it up, and if you touch it, you should hear a spark. Or the other thing you can do is you can bring it near small pieces of paper, and you'll see you can pick up the pieces of paper. They'll move. You don't know it's charged. That's charging by induction. Questions so far? Let me check that kind of button. Okay, so I got quite a bit of time. So I have a couple more slides, and I'll probably talk about the other stuff next week. But I want to ask you a question based on what we've talked about here. Let me erase the book. Let me leave this up here. Somebody does an experiment. 5 styrofoam balls are suspended from insulating threads. Several experiments are performed on the balls, and the following observations were made. Ball A attracts ball B, but repels ball C. Ball D attracts B and has no effect on E. And in the third experiment, a negatively charged rod attracts both A and E. And the question is, what is the charge on each ball? What can we say about the charge on each ball? I'll give you a minute to think about it. You can respond in the chat what you think, or you can just blurt it out loud. Whatever you feel comfortable with. You tell me which one's positive, which one's negative. So D and E have to be uncharged. Let me write this down. I just want to write down, and then we'll see if what the class says makes sense. So D and E is uncharged. That's what I see so far. That's what I've been told. So I'm going to write down what I'm told. David, I'll wait. I'm just going to write this down for now. I'm going to see what else people say. Anybody else want to say anything? What about the other three balls? Oh, I'm sorry. I didn't see that. A, E, and C are positive. Wait, so we get a conflict. So A, C, and E are positive. Before I go on, what do you say about B? So we have a conflict here. We have to resolve that. A has to be positive, or at least A and C. Okay. But this one's in conflict. What do we say about this one? Now, what about B then? Okay. What about B? B is negative? Okay, so let's say B is negative. Okay. So I see that some people are saying that this is uncharged. Remember this statement, that a charged object is always attracted to an uncharged object. And it doesn't matter, yeah, D is uncharged. It doesn't matter what the material is. So if I take object D and I bring it next to E and there's no effect, what's that mean? Neither one of them can be charged. So this one can't be in that list. Now, does this list all make sense? Well, A attracts B. That means A and B have to have opposite charge. But we know from the third test, a negatively charged rod attracts A. That means A is positive. Okay, the fact that the negatively charged rod attracts A tells you right away this is positive. And since these two repel, this has to be positive. And since these two attract, this has to be negative. And since these two don't produce any effect on each other, that means they have to be in charge. That's because of this statement. Does that all make sense? The B has to be charged just because of the fact that D attracts B. And it attracts A too. But we know that A is charged because A repels C. A charged object and an uncharged object will never repel each other. They will always attract. Now, if you do, can't remember if I did it with you guys or with my lab class. So if you do the same experiment with a can, or you put a can horizontally in the ground, and you bring this, you'll see a more pronounced effect than with a insulator. Okay, so you can, if you bring this close, you'll see this thing will roll really fast. So that's a fun thing to try. Just bring a charged rod next to a can, and you'll see the traction. It's a pretty strong effect. If you bring it too close, the can will touch your rod. And by the way, if the can touches the rod, you might think, oh, I just transferred charge to the can. Actually, it's pretty hard to do that. You actually have to rub the can quite a bit in order to transfer the charge. Do you folks have any questions so far about what I've said? Anything unclear about what I said? Yeah, what's your question, David? Insulators and conductors behave. Yeah, when they're isolated, they don't do anything, right? I mean, they're just, from an electrical point of view. Yeah, so in fact, in this experiment, I asked the question, what if the balls are metal? You're going to get the same results. Or regarding creating a dipole moment. Yeah, the dipole moment for a conductor, it's within the molecule, right? But I'm sorry. For the insulator, the dipole moment's created in the molecule. With a conductor, it's really done with the free electrons and the atoms or molecules that make up the metal. It is a bigger effect with the conductors. It is a bigger effect. You do form a dipole moment with the conductor. It is a bigger effect because of the fact that the electrons are free to move. So L is going to be bigger. The other difference is that in an insulator, it's within the molecule itself, whereas with a conductor, it's within the entire object. Right? So if I bring a negatively charged rod here, then the minus side will move to the other side of the object. So it'll happen over the entire extent of the object, whereas in an insulator, it just happens over the molecule. So yeah, this effect is bigger here. But we normally talk about the dipole moment within an insulator. We really don't talk about the dipole moment within a conductor. Can a molar molecule produce a large enough difference to create a measurable force? Well, I mean, I guess what do you mean by measurable? Because if you take a comb, what do you mean by measurable? Because if you take a comb, rub it on your head and bring it by a stream of water coming out of your faucet, you can see the water bend. To me, that's measurable. Well, a measurable force within the two particles, within the two sides. I don't know how you would measure that because it's within the medium. I think you can only calculate it. I don't have a feel for how big that number would be. So I couldn't really. I really couldn't. It's hard for me to answer that question. You couldn't measure it, but you can probably calculate it. But I just don't have a feeling for how big that number would be. That's a good question. Yeah, you'd have to do it with one water molecule alone, and you'd look at, since you know the dipole moment, and you want to look at the force between the charges. I mean, basically you have to have an idea what is the separation between the plus and minus charge. You can do a real quick back of the envelope calculation. If you know, and the chemists know this, the separation between the positive and negative charge in the molecule, Use Coulomb's law, it'll give you an idea. My guess is it's not going to be a very large, it's going to be a pretty small number. But like I said, I haven't done the calculation. It is a good question. So you can do a real simple calculation by looking at the average separation between the positive and negative charge in the water molecule and apply Coulomb's law. You can try that. Yeah, if you scale it up to a bunch of molecules, it should add up. That's right. But then, you got to take into account too that the molecules interact with each other too. It's more complicated. When you start getting a large collection of particles, then you have to take into account the interaction between molecules. Yeah, it's fluid mechanics and fluid dynamics. It's hard. Yeah, you guys are asking good questions, and I don't have a real feeling for numerically with these values. But you can do it for one molecule. And then if you have Avogadro's number of molecules, how big is that force? But my concern, though, would be there's other forces involved that might reduce the overall force. Let me check the time real quick, because I have 12:30 left. Okay. So again, you have to build the electroscope, and you have to build this guy by this day. So the video you just upload on the Canvas. I set up Canvas so you can just upload the video, and then I'm just going to watch your videos. Basically, for these videos, I just want to see that they work, and I want to see your face in the video, pretty much. It's out of 20 points. It says not. I expect the grades to be pretty high if I turn them in on time. Okay. Ian, I'm not sure what you mean. Are they separate videos? Oh, I mean for the two objects. You can do them however you want. You can do it as one video, or you can do them separate. I mean, you can make separate videos and make them into one. I did that with our lecture we had the other day. I accidentally stopped my video, and I just put it in. Uploaded the two videos into a video program in Word and on the PC, and I just saved it and I was done. You will have the lab kits before the second video. You should have the lab kits next week. Okay. No, you'll submit the videos on Canvas, just like you would submit your exams or you submit an assignment on Canvas. There's a place where you can upload the video. Yeah, the first video, you don't need the lab kits at all. Because the lab kits don't have this. The lab kits doesn't have the jar or anything. You'll need to do with stuff you have at home. Okay. So the first video, you'll just show me, and you can break it up into two videos, however you want to do it. You can upload two files, one file, depending how comfortable you are messing around with the videos. Just showing me the two objects that they work, that's it. And then the second video is going to be on, basically you demonstrating what's asked of you in the lab and then explaining it. Does that make sense? Okay. And if you're, some of this stuff is online too. I mean, you'll see various demonstrations on electrostatics online. So you can give you an idea of how to make the video. I don't expect, Hollywood production, okay? Just like this is not, what I'm doing right now is not a Hollywood production. Okay. As long as I can see that you understand what's going on, that's really what matters. Okay. So I'm going to end this right here, take 10 minutes, and then start my next class. And again, if you have questions, if you have lab questions, I know some folks like to use Discord, but if some of you folks who are not on Discord, go ahead and use the discussion board and ask questions. Find a place to ask a question, okay, regarding the labs. We'll try to answer. We want to help each other out. Okay. All right, I'm going to stop here. Oh, you're welcome. Let me stop the share here. Let's see you on Monday.